Hello, welcome back to Petrophysics Rocks. We're well into our series now of Petrophysics for Dummies. It's not quite as exciting as a Netflix box set, I guess, but hopefully I have shown so far how we measure the amount of oil in our reservoirs and the rock types that they're in. And now the next important thing we need to know is, can we get it out? How does the reservoir fluid flow through the pore space? Here you see another electronical derivation cartoon of how fluid flows through. These are sand grains here, what we're interested in is the rate at which fluid can flow through the sand grains and the rate at which we can get it out. Some rock is very, very impermeable, so it's quite difficult to flow through it. And in fact, some rocks we rely on impermeable rocks capping the reservoir to keep the hydrocarbons, the oil in the reservoir, so that we can come along and take it out through these more permeable bits. Okay, well, without further ado, let's crack on to the next section, which is called permeability, and let's see how we get on with that. Okay.
So, we've covered the rock type, the volume, and the fluid types, and we've sort of touched on a couple of occasions on the permeability story, the ability of the rock to flow. And that's what I'd like to touch on now, actually, just cover that with a number of ways of getting at the flowing properties of rock. I guess the primary and direct measurement, of course, is the core measurement. You remember we cut some plugs in our conventionally recovered core, and here I've got a couple of plugs, one sandstone with quite small pore space in it, one sandstone with quite big pore space in it. Now, to measure permeability across there, if you can imagine yourself blowing on one end of this core plug, and you can imagine that if the pore space in the top one is quite tight, quite small, you'd have to blow quite hard to get air out at the other end. Whereas the lower one here, it's a bit easier, and you can see that you can imagine a much easier permeability pathway through here. So if you were to measure pressure at various points along here, in this top plug, you'd be really pressuring up this early part of the plug, and not much of that air would be getting through to the end part of the plug, so there'd be quite a large pressure differential. Whereas in this lower plug, where it's easier, you're putting in some pressure, but it obviously doesn't build up that much because it transmits quite easily to the far end of the plug, and so the pressure differential is actually quite small. So that's what we're talking about here, the difference in pressure from one end to another. And when it's difficult, there's quite a large pressure drop, and we say there's a low permeability. And when it's easy, there's a small pressure differential, and there's a high permeability. If you'd like to Google Darcy, there's an equation there that you can use to calculate permeability from cross-sectional area and pressure differentials. But this is the concept that I just want to get across at the moment. Easy is high permeability, and this hard-working stuff up here is low permeability. Now that's a direct measurement, and as I've already said, it's quite difficult to get core everywhere, so a lot of our time is spent trying to find predictors of permeability from other measurements. And one of the other measurements that I'd like to talk about now, potentially, is the NMR measurement, which is often very good at providing estimates of permeability.